Hey everyone, welcome back to physics. This is going to be lecture 28 of the course. And in this section, we're going to shift from our discussion of kinetic energy to the contrary idea of potential energy. We're going to fold potential energy in with the idea of conservation or kinetic energy and arrive at this broader concept of energy conservation. And so in this first section, we're going to look at sort of the simplest to grasp aspect of potential energy, and that would be gravitational potential energy. So let's go ahead and jump into it. We'll call this section 6.1 gravitational potential energy. All right, so we just finished a whole kind of a longer section on kinetic energy. And we kind of discussed there that kinetic energy was the energy of motion. Kinetic energy, this is like the energy of motion. Okay, and what we want to talk about next is potential energy. And this is a different kind of concept, but I mean, obviously they're related. This is more like you can kind of think of this as the energy of position, right? So an object will have energy if it's in motion, but it can also have a kind of energy when it's placed in a certain kind of position. Okay, and so like just the simplest example, if I take a stone and I lift it up into the air, maybe it's at a certain height from the ground. If I lift the stone in the air, I know that the second I let go of it, right? The second I let go of this stone, it's going to acquire velocity, right? It's going to speed up, and it's going to acquire velocity in the downward direction due to gravity, right? So as soon as I let go of it, it's going to begin moving. Now, while the stone is in the air, it has what we call potential energy. Right, and we'll get into this obviously in a lot more detail in a bit, but this is just kind of the key observation here. While the stone is in the air, it has potential energy, right? The second I let go of it, it begins to acquire kinetic energy. And you can kind of think of it like it begins to convert potential energy into kinetic energy. So when I let go, it begins to acquire kinetic energy, right? And you can think of it as acquiring this kinetic energy sort of from this storehouse of potential energy. Okay, well, we'll leave that off for now. We'll get to that. So while the rock is in the air, it has positional energy. It has kind of like the possibility of work to be done is present, right? So while it's in the air, we know what'll happen the second I let go of it, and it has this kind of potential, right? So in this section, I mean, there are different kinds of potential energy, but in this section, we're going to focus on potential energy caused by gravitation. We'll focus here on potential energy from gravity. Okay, I think in the next section we'll talk about elastic potential energy, which is another kind of potential energy. Okay, all right, and so let's go ahead and start deriving some concepts here. All right, so we know that the work done by gravity on a body falling from a height, we know what that quantity is, right? So a body falling from a height of like y2 to y1, the work done by, we'll say, gravity, I'll write grav here, we know that that's equal to the force, it's equal to force times a displacement. And in the case of the work done by gravity, the force involved is the weight, right? The weight of the body. And the displacement in this case would be y1, the second position, minus y2. Right? Okay, and so if we just expand this a little bit, we get mg y1 minus y2, and we can see then that the work done by gravity is mgy1 minus mgy2. Okay. And so, like, for example, if we a 100 kilogram particle falling from 10 meters, a 100 kilogram particle falling from 10 meters. Well, what's the work done by gravity? The work done by gravity in this case is, again, mgy1 minus mgy2. Okay, and so it's equal to 100 kilograms times 9.8 meters per second squared times 10 meters, where it starts out, minus 100 kilograms times 9.8 meters per second squared times 0 meters, we'll say, because it presumably lands on the ground, right? And you crank this out, so this is 9,800 joules. This is 0 joules, and so the work done by gravity in this specific example of a 100 kilogram particle falling 10 meters is 9,800 joules. Right? So we can express the gravitational potential energy associated with the position of the particle at the beginning of the move, where y1 equals 10 meters. We can express this potential this is kind of like our potential energy, right? We can express the beginning piece of this work using this: U equals mgy1. Right, and this is going to be what we use when we think of potential energy. This will be the notation we use, will be U, and mgy1 being the initial position. In this case, the initial position of the experiment we described is the particle 10 meters off the ground. Okay, and so this is what we mean by, this is what we can use to calculate the potential energy, gravitational potential energy. Okay. All right, very good. So that being the case, we can talk about the change in potential energy. So the change in the potential energy can be, we'll say, obtained by the following. So we could say, so the work done by gravity is equal to U1 minus U2. Right, the potential energy at the starting point minus potential energy at the ending point. And this would be like U1 minus U2, but a better way to write it would be negative U2 minus U1. And we'll call this negative delta U. Now, the negative is very important, right? You got to make sure you understand which direction are these quantities oriented towards, right? So when the body is moving up, let's write this down. Body moving up. In the case of gravitational energy, when the body is moving up, the work done by gravity is negative. Okay. And then the reverse is true when the body is moving down, then the work done by gravity is positive. Okay. And so that's just the way we kind of set it up. And it makes sense that way, right? Gravity is a force that pulls things toward the Earth, right? Downward, right? And so if a body is moving upward, then this piece here is going to be, altogether will be negative. If the body is moving downward, then this piece here will be positive. Okay? And so this is how we describe potential energy. Potential energy is U equals, gravitational potential energy is U is equal to M times G times Y. Okay, where Y is taken to be the position. Okay. All right, so what we want to talk, so that's kind of our rough definition. And we'll do plenty of examples, so don't worry about that. We'll get to lots of examples here. But what I want to do next is kind of quick, because most of the examples are going to rely on this. I want to quickly connect the idea of potential energy that we just developed to what we've already been discussing, and that's the kinetic energy. And so this is going to lead us to the conservation of what we call mechanical energy. And so we'll develop this in total here. So conservation of mechanical energy. This is a big idea. It's an idea that's not unintuitive. But it's a big idea of the universe. It's an interesting way to look at things. So let's assume, and the conservation of mechanical energy requires that we assume that a body's weight is the only force acting on it. Okay, so assume that a body's weight is the only force acting on it. I.e., let's just let the body be in free fall, right? So i.e., a body in free fall, right? Gravity is the only force. Okay. Right, and we should say with no air resistance. Okay. All right. And so let's assume at y1 we have speed v1, and at y2 we have speed v2, right? And so whatever's happening, we're flying through the air. For the simplest example, let's just imagine like a ball dropping, right? Okay, at y1 we have a certain speed, and at y2 we have another speed. Okay, and now let's recall the work energy theorem. What did the work energy theorem say from prior sections? The work energy theorem said that the total work is equal to the change in the kinetic energy, which in our way of describing that we said was K2 minus K1. So the final kinetic energy minus the initial kinetic energy. And then we defined kinetic energy to be 1/2 mv1 squared minus 1/2 mv2 squared, right? So that's what we thought about in the case of the work energy theorem and kinetic energy. Now, what we've just discussed is a different kind of work, right? Okay, we just described a different kind of work, and that is the work done by gravity. Okay, so we just described W grav, which we said was equal to negative delta U, i.e. the negative change in potential energy, which we said would be the same as U1 minus U2, which we know is mgy1 minus mgy2. Okay, so we just got done talking this through. Okay, so we have this idea here, and then we also have this one here that from the work energy theorem. So where this is K2 minus K1 equals 1/2 mv2 squared minus 1/2 mv1 squared. And so this is two ways to describe work. Now, if gravity is the only force acting on a body, then we can equate these two, can't we? Right? And if gravity is the only force acting on a body, then the total work is down here is the same as just work being done by gravity, and here's again just work being done by gravity. So we could equate these two. We can say K2 minus K1 equals U1 minus U2, right? So the change in the kinetic energy, this is saying is the change in the kinetic energy is equal to the negative change in the potential energy, right? And so we can kind of reorganize this and instead write K1 plus U1 equals K2 plus U2. Okay, and so what this is saying is that the sum of the kinetic energy and the potential energy at position 1 is equal to the sum of the kinetic energy and the potential energy at position 2. Okay, and so this is the total mechanical energy. So K plus U is what we call the total mechanical energy. And what this is describing is the principle of the conservation of mechanical energy. Okay, so in particular, we would say E1, the energy at position 1, is equal to K1 plus U1. So this is the energy at position 1. And obviously E2 equal K2 plus U2. That's the energy at position 2. Okay. And so when gravity is the only force involved, then the total mechanical energy is constant between these two positions. When G is the only force, then the total mechanical energy is constant. And another way to say that is conserved. Right? Meaning as the particle or object changes position from 1 to 2, this equation remains constant. Okay. Let's see what this kind of looks like, in practice. And obviously this is not an experimental course, so I won't be able to actually show you that, but a way to look at it is just to kind of do a thought experiment of just throwing a ball up in the air. Right, so let's say we start with a ball that's in flight, right? And air resistance is negligible. So we'll say here that the ball is moving upward. Right, so it's got some velocity in the positive direction, in the upward direction. And what's happening here is, we all know that the kinetic energy is decreasing here, meaning kinetic energy is 1/2 mv squared. Now, if the ball is in motion upward and gravity is the only force acting on it, it's going to be slowing down. So the kinetic energy as the ball moves upward is decreasing, but the ball is gaining height off of the ground, and so that means the potential energy is increasing. Let's just use K and U. So the kinetic energy is decreasing and U is increasing as the ball is moving upward, right? Remember, gravity is the only thing acting on it. And everybody knows from experience, you throw a ball up in the air, it'll go up, sure, but it slows down as it goes up, doesn't it? Right? So the way to think about this is that the kinetic energy is being converted to potential energy. So K is being converted to U. As the ball slows down, it gets higher and higher, and the energy is conserved, right? So as much energy as was present at the beginning of the thing is still present at the end, but it's just been transmitted into potential energy. Now, when the ball hits its peak trajectory, so the ball at peak trajectory, right? So that means it's all the way up and as high as it's going to go. At that point, their velocity is equal to 0, right? And so that means the kinetic energy is equal to 0, right, at the peak trajectory. And all of the kinetic energy at this point has been transferred into the potential energy. So the potential energy is at maximum. Okay. This is at the peak. So here you've got the ball moving up. Here you've got the ball at the top of its trajectory. And then, of course, we know what comes next. The ball falls back to Earth. Right, so it begins to acquire some kind of a velocity downward. Right? And then what's happening? What's happening over here is the reverse of what's happening here. So in this case, the ball will acquire velocity. So the kinetic energy will increase. The potential energy will decrease. Right? And over here, we said kinetic energy is being converted to potential energy. The reverse is true over here. U is being converted to K. Okay. And so this is the idea that the energy is constant. You throw the ball up with a certain amount of force. It has a velocity as soon as it leaves your hand. And that means it has a certain amount of kinetic energy. It also has a certain amount of potential energy. Those two quantities one will transmit into the other, and then the reverse will happen. It'll transmit back. All right, so let's kind of walk through this experiment or this example with some actual numbers. Okay, let's do an experiment here with some actual numbers. So, an example: you throw a ball. And we'll say the mass there is 0.145 kilograms into the air with an initial velocity of 20 meters per second. Okay. So then how high does the ball go? How high does the ball get? And so I've got, the picture is pretty straightforward. We've got this ball. Initial velocity is 20 meters per second. We'll assume it just starts at ground level. Okay. And so then the question is, how high does this thing go? So our target variable in this case is the displacement. Right, and we'll just denote that y2 minus y1, right? So y2 will be, we can think of it like this. A lot of times when you're dealing with conservation of energy type problems, you want to coordinatize based on points in the trajectory or the displacement, right? And so we'll say that y2 is the height that it achieves, and then y1 will be at the bottom, which is 0. So the question is, how high does this thing get? So it's going to go up, and then it's going to come back down. And how high does it go? Right, and so there's different ways to solve this. We're going to use the conservation of mechanical energy idea that we just developed naturally. And so we would say the potential energy at position 1 is equal to mgy1, which we know is 0 because the position is 0. So mass times gravity times 0 is 0. Okay. What's the kinetic energy at position 1? Well, it's 1/2 mv1 squared, and so 1/2 0.145 kilograms times 20 meters per second squared, and we see that K1, when we multiply all this together, we get 29 joules. Okay. What about U2? What's the potential energy at position 2? I'll put those over here. U2 is unknown, right? Because U2 is equal to mgy2. Y2 is specifically the variable we're targeting, and so this is like unknown. What's the kinetic energy at position 2? Well, it's 1/2 mv2 squared. Well, the mass is 20 or 0.145 kilograms. The velocity at position 2, so like up here. So down here, the velocity starts out at 20 meters per second. It shoots up into the sky. It's going to slow down, slow down, slow down, slow down, come to a stop at the peak height. And so the velocity at position 2 is actually equal to 0. So this whole thing is equal to 0 joules as well. Okay. And so our equation, remember, is K1 plus U1 equals K2 plus U2. Now we know that U1 is equal to 0, and we know that K2 is also equal to 0. And so that means what we really are dealing with is K1 equals U2. So the initial kinetic velocity must be equal to the final potential velocity. And this is really just describing the trip up. Okay. Okay, and we actually calculated K1 already, and so we know that U2 is equal to 29 joules. And so U2 is mgy2. So mgy2 is equal to 29 joules. Right? And so we can see that I can easily solve for y2 now. So y2, the height that the ball reaches here, must be equal to 29 joules, the kinetic energy at the starting point down here, divided by m and g. So 29 joules divided by 0.145 kilograms divided by 9.8 meters per second squared. And you do that math and you get about, what, 20.4 meters. Okay, so the ball is going to go approximately 20.4 meters into the air. Right, now remember, the only force acting on it once the ball is airborne is gravity, right? So there's some initial force that's applied, obviously, to create the initial velocity, but after that, it's basically free fall. You know, and so under those conditions, we know that K1 plus U1 equals K2 plus U2, and we can calculate this precisely using nothing more than this conservation of mechanical energy. Okay, and so that's what happens. That's how this can be used when you're in a situation where all of the forces other than gravity are zero. But what happens to this whole picture when other forces are present? So what happens when gravity is not the only force at work? So what happens when forces other than gravity are at work? Okay. Well, if other forces are at work, we can say that the total work is equal to the work done by gravity plus the work done by these other forces, right? This is natural, right? The total work. I mean, when we were talking about work previously, we did this kind of thing. We would identify the work done by all the forces, sum them up like this. Okay. And so we could say that, and you know, we just previously saw that the total work is equal to the change in kinetic energy. And so we also have that W total equals W due to gravity plus W other, which is equal to the change in kinetic energy. Okay, and of course we know that the work done by gravity is equal to U1 minus U2, right? We just talked about that. Right, so we can combine these things. We can combine these things, right? Specifically, let's take this thing here and plug it in right there. And so what do we see? We see that U1 minus U2 plus W other is equal to K2 minus K1. And then this can be rearranged. This isn't the optimal arrangement, in my opinion. The better way to arrangement is to arrange it based on the timing. And so let's say K1 plus U1, just like before, is equal to K2 plus U2, but now we're going to retain this work other over here. Okay, so you've got kind of the same equation. You've got the total mechanical energy, but now you've also got this work other term. You got this other piece in here. Okay, so what does this mean? Well, we can rearrange this slightly again just to kind of extract the meaning from it a little clearer. We could say that work other is equal to K2 plus U2 minus K1 plus U1. Okay, so what does this mean? What does this mean? Well, the work done by all of the other forces is captured by this, right? The work done by all of the other forces, i.e. not gravity, is going to be equal to the change in the total mechanical energy of the system. Right? This is the total mechanical energy of the system, ending and beginning. Right? So you subtract those two things, that's the change in the total mechanical energy of the system. Right? So specifically, we would say that when work other is greater than 0, what does that tell me about this? Well, this side is greater than 0. That means this side must be greater than 0. right? So the implication is that K2 plus U2 is greater than K1 plus U1, meaning the mechanical energy at the ending is larger than the mechanical energy at the beginning, right? So the system's energy increases. Makes sense. There's another force involved. There's some other force acting on the system, inserting energy into the system. So what happens when work other is less than 0? Well, the reverse, right? That means K2 plus U2 must be less than K1 plus U1, which means that the energy at the end of the system, at the ending point, is less than the energy at the beginning point, right? So the system's energy decreases. Okay, and then of course, so those are the first two, and then the option we started with is really when work other equals 0, and then of course you see that K2 plus U2 equals K1 plus U1, and in this case energy is constant. Okay, so this is the special case. This is the case we started with, but indeed, like these other cases, exist as well. Okay. But when there are no other forces involved besides gravity, then the total mechanical energy of the system is constant, and we say that the energy is conserved. Okay. All right. Very good. Let's take a look at an example here, and let's kind of. I think we're gonna kind of go back to the example we just worked through of the ball flying through the air. And so, but we're going to modify it slightly so that there are other forces involved. Okay, so I'll say you throw a ball upward at 20 meters per second. It leaves your hand at 0.5 meters. Okay. Now, ignoring air resistance, find the force your hand exerts on the ball and the speed of the ball 15 meters above where it leaves your hand. Okay, all right, so in this case, there is an other force, right? The other force is the hand force, the throwing force. So the other force here equals the throwing force. Okay, so that's what kind of differentiates this particular example from the simpler example that we started with. Okay, and so what we want to do is we want to kind of think of the ball's motion in 3 stages. I think this is usually how, well, not usually, I mean very often this is how these things go. We'll think of the first position, y1, as being, well, there's really three positions we're interested in. So we got this y1, and then I say we have a y2 also, and then we have a y3. Now, there are different ways to coordinatize this. How you choose to coordinatize the problem could change how you work the problem out. I'm gonna coordinatize it in a certain way. I'm gonna say that y2 is where the ball leaves my hand, and it's going to be at 0 meters. Okay, and then I'm gonna have the point y1 be where the ball is in my hand at rest right before the throw. And so if the ball, it says it leaves your hand at 5 meters, so your hand must move 5 meters between resting and releasing the ball. And so I'm going to set this equal to negative 0.5 meters. Right? So that's a 5 meter move. The ball acquires all of its velocity here, and then here it's in free fall from y2 up to y3. And y3 is 15 meters. right? And so this is where the ball leaves hand. And this is where the ball's at rest. And obviously 15 meters is the height that we just happen to be interested in. Okay. Now, it's very useful. It's very informative. It's usually a good idea to kind of think through what's going on with the mechanical energy at each of these intervals, because depending on what's happening with the energy, that could obviously influence how you choose to solve this problem. And so when the ball leaves your hand, this is kind of the easiest one. So let's think about E as the total mechanical energy, and that we know is partially kinetic energy and partially potential energy. So when the ball leaves your hand, we will say that the potential energy is 0, right? Because like it's in your hand. It's just an instant, a split second away from your hand, so it has no potential energy yet. But it does have energy because it's moving fairly quickly, right? And specifically, it has kinetic energy. Right, so it's got all this kinetic energy, which is the sum total of its energy, because it has no potential energy at the starting point. Now, as the ball moves up, this little histogram is going to change. Right, as the ball moves up, it's going to retain all of the same amount of energy, because between y2 and y3, the only force acting on it is gravity. So the energy will stay the same, and apologies, I got to kind of go up into my text here. But the total energy is going to stay the same, but we know that as it moves upward, it's going to slow down. So the kinetic energy is going to decrease. And as it moves upwards, it gains height, and it specifically gains potential energy. And so maybe the kinetic energy comes down a bit, but the potential energy climbs. All right, so between 2 and 3, K is being converted to U. Kinetic is being converted to potential. Okay. And then what's happening at Y1? Well, Y1 is a little bit interesting, because like technically we've said that the potential energy is 0 at the moment when the ball leaves the hand. So actually the potential energy has to be a little bit negative here. As we'll see, it pops out of the equation. So it just actually has a little bit of negative energy. But the kinetic energy is certainly 0 at the resting point below where the ball leaves your hand. Okay. All right. So let's talk through all of the pieces of energy. So there's really kind of 2 questions we're being asked. First question is, find the force your hand exerts on the ball. And so that's what we're interested in. So we'll start with that. To identify the hand force. That's the first part. Right, so let's think about what the energy levels are from here to here, from Y1 to Y2. So this is specifically Y1 to Y2 that we're talking about. So kinetic energy, K1, it's 1/2 mv1 squared, and we know that the velocity at Y1 is 0, so the kinetic energy is 0. We already drew it out here also. Right, what about the potential energy there? Well, we have mgy1. Okay, and so this would be 0.145 kilograms times 9.8 meters per second squared times y1. The position is actually negative 0.5 meters. So if you multiply all of this together, you will see that you actually have a little bit of negative potential energy here, negative 0.071 joules. Okay, and this is a product of how we've chosen to coordinatize this thing. Okay. And so if we had set 0 to be y1, then y2 would have not 0 potential energy. It'd have a little bit of potential energy, right? So you have to choose one or the other. Either it's 0 at y2 or it's 0 at y1, whichever you prefer. You'll get the same answer either way, but the numbers will look different in the interim. Okay. And what about K2? What's the potential energy at K2? Well, or sorry, the kinetic energy at K2. Well, we know it's high, right? Because the ball's moving rapidly. It's leaving our hand very rapidly. So it's 1/2 mv2 squared. So 1/2 0.145 kilograms times the velocity at position 2 is 20 meters per second. Square that. And you do all this, and we've done this problem already, so we know that it's 29 joules. And then what's the potential energy at position 2? Well, we know that's 0, right? We've already discussed that. That's how we set this up. mgy2 is equal to 0. Okay, so we've got 0 joules, slightly negative number, 29 joules, and then 0 joules. Okay, and so K1 plus U1 equals K2 plus U2. Oh, sorry. Hold on. Plus work other. Hold on. We'll just go to the next page. We will go to the next page. So we've got K1 plus K2. Now, the hand is a force in this, right? Work other equals K2 plus U2. So this would be a U. Wait, what? K1 plus U1. Sorry. Apologies. K1 plus U1 plus work other equals K2 plus U2. Okay. All right, and so so this work other, this is the hand that accelerates the ball. Okay, and so that's really what we're solving for. So let's just set it up like this. Work other is equal to K2 plus U2 minus K1 plus U1. Right, now we plug our quantities in. So this is equal to 29 joules plus 0 joules minus, and then this would be 0 joules minus, what was it, 0.071 joules. Right, just kind of going back to the previous sheet, pulling those numbers forward. And so 29 plus 0.071 is equal to 29.71. Okay, 0.071. Yeah, no, that's fine. I think this is 0.7. Okay. And so the work being done by the other force, i.e. the hand, is this guy right here. Okay. And so work other is equal to the force times the displacement, right, which in this case is equal to the force times y2 minus y1. Okay, we know what these quantities are. We want to solve for the force. This is the part we're interested in. Okay, so the force here is equal to the work being done by the other forces divided by y2 minus y1. All right, so in this case, it's 29.7 joules divided by, what's y2? Well, we set that to be 0 meters. And then what's y1? Negative 0.5 meters. Right, so this is 29.7 divided by 0.5, and you get 59 joules. Right, so the force that's being done by the hand, that, you know, so there's a certain amount of work, it accelerates this ball over this half meter from 0 up to 20 meters per second. That force is 59, this is newtons, sorry, 59 newtons. All right, so the ball leaves the hand at 20 meters per second because the 59 Newton force is exerted on it by the hand. Okay. So again, just a straightforward application of this thing here, right? You just have to recognize that the other force involved in the scenario is the hand force, is the hand pushing the ball. Okay. Now, the other part of the question is we want to know the speed of the ball at 15 meters. So to find the speed of the ball, and we'll say y3 equals 15 meters, what do we do there? Well, again, you know, the thing to notice here is that when we go from y2 to y3, the hand is no longer involved in the process. The only force involved in the process is gravity. So we're in free fall, so energy is conserved. So from y2 to y3, energy is conserved, right? And so that means we can just use K2 plus U2 equals K1 plus U1. Oh, sorry, K3 actually, and K2. Apologies, there we go. So just make sure those indices are right. And we've already calculated K2 and U2, but what about K3 and U3? Well, U3 is equal to mgy3, right? And so m is 0.145 kilograms, and g is 9.8 meters per second squared. And what's y3? Well, we're told that it's 15 meters. That's the height we're interested in, right? So we know that. So we know that the potential energy at that point is the product of these three numbers, which turns out to be 21.3 joules. Okay, so we've got that part. Now, what about K3? Well, this is 1/2 mv3 squared, and this is specifically what we're looking for, v3. So we don't really know this one. This one is unknown. But we do know, from this equation here, right, we can solve for K3 because we know everything else, don't we? Right, so K3 is equal to K2 plus U2 minus U3. We know all these quantities. So K2 we found on the previous page is 29 joules. The potential energy at position 2 was 0. And then we just found U3 to be 21.3 joules. So that means the kinetic energy at position 3 must be this difference, 29 minus 21.3, which we see as 7.7. Okay, so the nice thing is we know that K3 equals 7.7 joules, which is 1/2 mv3 squared. And so we can solve for v3. v3 is equal to the square root of 7.7 joules times 2 divided by the mass, which is 0.145 kilograms. All right, technically this is a square root, so plus or minus. And we get, when you do this division, you get plus or minus 10 meters per second. Now, sometimes the plus and the minus, one of them makes sense and is useful and the other is not. In this case, they're both meaningful, right? So in this case, the velocity at 0.3 is positive on the way up, and the velocity of v3 is negative on the way down, right? So here's your y3 equals 15 meters. Ball's going to go up and then come back down. So it's going to hit that height twice. Here it's going 10 meters per second. Here it's going negative 10 meters per second. All right, so both of them have meaning in this case. Now, sometimes that's not the case, but in this particular example, that is the meaning. Very good. Okay. All right. So up until this point, we've really just considered the sort of simple case of, I guess you'd call it one-dimensional motion, right? I.e. balls flying up or balls falling down, in sort of a more or less vertical path, right? But what happens if the path is curved, right? So what happens if instead you have a picture that looks more like this, right? You've got some height here and some kind of a particle, right? And that thing's not falling straight down to the ground. Instead, it's going to fall kind of in a curve, like maybe, it falls like this, we'll say. Whatever kind of curve. Right now, there's some, if you think about like what's going on here, for example, there's some force that must be pushing it off this trajectory. If there were no forces, maybe it would be falling straight down, but maybe you've got some force acting on it that's kind of the other force. But we know that gravity, right, always operates like this. Right? It's always downward. Okay. And so the fact that the particle, specifically in this lecture, we are talking only about the work done by gravity. We're talking about potential energy caused by gravity. specifically. Now, this won't be necessarily true if we're talking about potential energy of other forms, but gravitational potential energy has this nice characteristic in that the work done by gravity is the same as if the body had been basically displaced vertically in a straight line, even if the path is curved like this, right? And you can see this if we kind of take the work gravity equation and sort of like make it more like vectors. So this is equal to the weight times the displacement. If we think of these as vectors, then the weight here is negative mg. It's a vector, and that's always in the j hat position. It's always in the y coordinate position, isn't it? And we know that's going to get dotted against the displacement vector, which we could think of as the change in the x coordinate times I hat plus the change in the y coordinate times j hat, right? And we know that when we dot this together, there's no I coordinate for gravity. There's just j, right? So this is going to be ignored, right? And basically the dot product here is just going to be the negative mg times the delta y. And it's all j hat, isn't it? Right? And so this just shows you that the work done by gravity is really, it doesn't care if the path is curved. It's just gonna act in exactly the same way as it does in 1D motion, right? If this box were falling straight down, the work done by gravity would be the same as if the box falls in some kind of a curve like this, right? Okay, so weight always acts downward. That's really the kind of the takeaway. So work always acts downward. So the work done by weight is always across a vertical displacement. Okay, right? So don't let, at least not in this section, don't let problems that have paths that are not perfectly vertical, don't let those throw you. And so just to give you an example of this, let's talk about the next problem, which is such a problem. Okay, so I'll draw the picture here first. Okay, and so I've got basically kind of like this kind of rampy thing, like a wall, smoothed out wall, and a ball that's sort of rolling down this thing. Okay, and then this is going to be cylindrical, right? So it's going to have a certain radius, we'll say. Okay, and I'm going to make the radius 3 meters. Okay, and so here's this is the picture, and then let's talk about what the question is. So you roll a ball down a ramp, okay, which has radius of 3 meters. Okay, the ball's mass, we'll get some numbers out here. The ball's mass is 25 kilograms, and it starts at rest. Okay, it starts at rest. We'll assume no friction. Okay, assume no friction. What is the speed at the bottom? What's the speed at the bottom of the ramp? And then secondarily, what is the magnitude of the normal force at the bottom of the ramp? Okay, all right. So this isn't exactly the same as things we've seen, right? The ball at first, given the way this is drawn and the fact that we know this is a vertical ramp, given the fact that we're talking about a radius here, it almost starts like it's in free fall, but then as it encounters the curvature of the ramp, it deviates from free fall, obviously, and another force comes into the picture, specifically the normal force, right? So when the ball is here, for example, we know that there's a normal force acting, right, to kind of counteract the weight of the ball, right? And so that being the case, we know that we're not dealing with a purely like conservative mechanical energy system here, right? So how can we solve this problem? Well, let's start by fleshing out the sort of, well, first of all, like let's talk about what's y1 and what's y2. We'll say that this is y1, right? And we'll say that this is y2. Really the only 2 points of interest here, right? At the beginning, when the ball is at rest, right before you let go of it, it's got all this potential energy, zero kinetic energy. And then at the bottom of the ramp, right, it's totally at the bottom. It is not going to fall any further. So it has no potential energy and all kinetic energy. We know that much. So let's think about the energy quantities. At K1, we just said the ball's at rest. Initially at rest, it says so. The ball starts at rest. So the kinetic energy is 0 joules at the onset. And what's the potential energy then? Well, it's mg y1. What is y1? Are we told? Well, we're told that the radius of the thing is 3 meters, and so that means it must be 3 meters to the bottom, right? So this is actually, let's see here. This is going to be like the mass of the ball, so 25 kilograms times 9.8 meters per second squared times 3 meters. Okay, so it's mgr. I'm just going to leave it as mgr for a second here. We'll come back to this. Right, we can actually calculate this, but just for the purposes of shuffling up our formulas, let's leave the abstract quantities in. What's K2? Well, K2 is kind of what we're trying to get to, isn't it? We'd like to know the velocity at the bottom of this thing, but we don't know. So it's 1/2 mv2 squared. We don't know v2. We know m, though. And what is u2? Well, that is the potential energy at the bottom of the ramp. Well, it's not going to fall any further, is it? It can't, and so that's 0. Okay. All right. So one of the things we can do is, even though there's a normal force involved here, in the vertical there's really just gravity at work, isn't there? Right? And so what we can do is we can say K1 plus U1 equals K2 plus U2. And so K1 is 0 and U2 is 0. Right? So U1 equals K2. Right? So the potential energy at the top is equal to the kinetic energy at the bottom. Okay. And so let's see what happens here. Right, so let's see. So this is telling me that 1/2 mv2 squared is equal to mgr. Okay, and so we can solve this. We know all of the quantities here except for v2. And so we can solve this for v2. We say v2 is equal to plus or minus the square root of mgr of 2 times mgr over m, and so this would be the square root of twice g times r, right? And so in this case that's 2 times 9.8 meters per second squared times 3 meters, and we see it's 7.67 meters per second. Right, so the ball is traveling at 7.7 meters per second squared by the time it hits the bottom of the ramp. Okay, now the second question is, what's the normal force at the bottom of the ramp? Right, what is the normal force at the bottom of the ramp? So if we think about what's happening with a free body diagram, at the bottom of the ramp, you've got the weight is equal to mg, this gravity force down, and then you've got the normal force opposing it. Okay. And so what you can say is kind of the sum of the forces in the y direction are, what are they? Well, you've got the normal force, and then you've got, which we'll say is positive being upward, and then you've got the negative weight force downward. Okay, and we know that's equal to mass times acceleration. Right, now because we're on a circular path, right, let's think about the acceleration as radial acceleration. Okay, so let's use ARAD. Okay, what is ARAD in this case? The radial acceleration is equal to, in this case, v2 squared divided by r. There's different ways to characterize radial acceleration. This is the way that kind of makes sense here. And we can calculate that quantity. We know 7.67 meters per second. We can square that, divide by 3 meters, and we get 19.6 meters per second squared. And so that's radial acceleration. And so we can kind of plug that in here. And what we see is that the normal force minus the weight is equal to the mass times the the radial acceleration. Okay, the normal force is what we're trying to solve for, right? So the normal force is equal to the weight plus this piece, this radial acceleration times the mass, right? And we have all of these quantities, right? So this is mg plus m arad, and so we've got what, 25 kilograms times 9.8 meters per second squared plus 25 kilograms times what we just calculated, which was 19.6 meters per second squared. Okay, and we can see that this part is just the weight of the person, which is 245 newtons. Obviously, the normal force is going to include that part of it, like your own weight, but you've been accelerated downward, right? And so there's this additional piece, and this additional piece is very significant, right, in this scenario. So 490 newtons, right? And so in total, the normal force is 735 newtons, right? And so the normal force at the bottom of this ramp that's being exerted on this ball is actually 3 times the ball's weight. Okay. All right, very good. Now, so then if you think about that, that's obviously going to snap back to 1 times the person's weight the instant the ball hits the horizontal part of the ramp, right? So the ball will weigh a ton, it'll hit, and then as soon as it levels out, all of that excess normal force will be gone. So kind of an interesting problem, tricky problem. Let's do one more example before we go. This is just a little bit more, it involves more other type of scenarios. And so in this example, a 12 kilogram block is slid up a ramp. And we'll say the ramp is inclined 30 degrees. And so the 12 kilogram block is slid up a ramp with an initial speed of 5 meters per second. And we'll say friction is not negligible. Okay, and the block is going to slide up the ramp somewhat, and then it's going to slide back down. So the block slides up 1.6 meters, comes to a stop, and then slides back down. Okay, well, so we haven't got to the question yet. Here's the scenario, though, and I'll just draw a little picture just to make sure this is clear. So you've got some kind of a ramp. It's inclined at 30 degrees. And you've got a block on this ramp, right, that's got some mass we're not told. The block is has an initial velocity of 5 meters per second. It slides up the thing a ways, and then it comes to a stop and kind of turns around and comes back down. Okay, and how far up it goes is told to us as 1.6 meters. All right, so the block slides up this thing, and then it comes back down. Right, and all we're told is the angle, the distance it goes. We're told that there's friction involved, so friction is obviously going to be an other force that's kind of coming into this. And the question is, there's two of them. First of all, find the magnitude of the friction force. Right, so friction is slowing this down somewhat. So find that. Let's figure out the magnitude of that thing. And then secondly, so it starts out at 0, but it shoots up at 5 meters per second, and it stops at the top and kind of starts coming back down. It picks up kinetic energy as it falls back down the ramp, and i.e. it has some velocity at the bottom. And so what is that velocity? Another way to say it is, how fast is the block moving when it gets to the bottom? Say it gets back to the bottom. Okay, all right, so there's really like these 3 points of motion, right? We start at the bottom, right? At rest, at bottom. And then it slides up a bit to point 2, which is the top of the ramp. Also at rest. And then it slides, and then point 3 is kind of like the same as point 1, really, but obviously a different scenario is being undertaken there, right? So that this is the bottom of the ramp again. Bottom of ramp again, but in motion. Okay. So you've kind of got this scenario. Starts out at rest, gets some initial velocity, slows down as it goes up the ramp, and then accelerates back down the ramp. Okay. And so because we're going to need, this is going to involve potential energy, we really do need to know how high this thing is. And so I think let's think about this as the height of the ramp. Can we figure that out quick? That's pretty simple, isn't it? 30 degrees, this is 1.6, we need to know h. Right, so the sine of 30 degrees is opposite over hypotenuse, so h over 1.6, and so h is 1.6 sine of 30 degrees, and if you do that math, you see that's 0.8 meters. Okay, we need that because, we're talking gravitational potential. We need to know the height. Okay. So let's think about our energy quantities between K and U. So what's the kinetic energy at position 1? Well, it's 1/2 mv1 squared. So it's 1/2, 12 kilograms. And then the velocity at position 1 is actually, so this is the initial velocity, right? So the block is shoved. And so we'll say its velocity at position 1 is 5 meters per second. I know that, so here I wrote at rest at bottom, but actually it's not at rest, right? It's at rest right before I kick it, but technically what we're interested in is the moment it's got that velocity, right? So the kinetic energy at the bottom is this, right? And so when I multiply all of that together, I get 150 joules. What's the potential energy at the bottom? Well, presumably it's at the bottom, right? So mgy1 would be 0, right? This is specifically y1 would be 0. So 0 joules at the bottom. What's the kinetic energy at the top? Well, it goes up the ramp, and then at the very top, it's pretty much got no velocity, right? So the kinetic energy is 0. All of the energy, mechanical energy has been transferred into potential energy. So K2 should be 0 joules. And then what about U2? Well, mgy2 is equal to 12 kilograms times 9.8 meters per second squared times the height, which is 0.8 meters. Multiply all that together and you see 94 joules. So it's got 94 joules of potential energy. Okay. All right. Now, because friction's involved, the equation we really need to use is K1 plus U1 plus work done by other forces is equal to K2 plus U2. Now, U1 is 0 and K2 is 0. So really, we have K1 plus work other equals U2. And we're looking for the friction force here, so work other is the one that we want. So we could say work other is U2 minus K1, whatever those quantities happen to be, which we have. Okay. So work other equals U2 minus K1. Now, in this case, the other force is the friction force, right? And so let's bring that into the, instead of work other, let's describe the force, let's describe the work as being the force times the displacement. So we'll say, so we're moving up the ramp, so friction is going to be in the negative direction. So I'm going to say negative F, and I'm just going to subscript it friction, times the displacement is equal to U2 minus K1. Okay, that's the work of the other force in this scenario is friction, right? And friction would be opposite the motion, and so it's negative. And so all of this can be tossed into an expression just for the friction force. So it's equal to negative, and then what is it? U2 minus K1 over S, which plugging all of this in, we get negative, and then it's what? U2 is 94 joules we found, and K1 is the initial kinetic energy, that's 150 joules. And then S, what's S? S is the displacement over which, the displacement over which the friction is active, and that's going to be the whole 1.6 meters, presumably, right? Okay, so you got this. Divide all this down, you're going to get a negative in here, but you got the negative outside, and so the friction force is going to be equal to 35 newtons. Okay, and so the magnitude of the force of friction in this case is 35 newtons. Okay, now the question of so that's the first part of the question. The second question says, how fast is the block moving when it gets to the bottom, right? When it gets to the bottom of the ramp, right? Remember, so now we're going from 2 down to 3. Okay. Now, there's different ways to do this. One of the ways to do this is to say, you know what? I'm going to go from 1 to 3. I'm not going to go from 2 to 3. I'm going to go from 1 to 3 because I've already calculated all the quantities for 1. And I know what the friction force is, right? So what thing you can say is you can say on the way back down, really the forces are all the same. The friction force is the same. It's just got a reverse orientation. And so the total work done between points 1 and 3 can be characterized as this work other equals twice the work done by friction, which we could say is negative 2 times the force of friction times the displacement. And this is just kind of thinking about, you got friction on the way up, you got friction on the way down, right? And it's always working opposite the motion, right? And so this is going to be negative 2. The force of friction we just found was 35 newtons. And the displacement is 1.6 meters, right? So we're doubling it, so everything gets doubled here. And so the total work other done between 1 and 3 is really negative 112 newtons. Or sorry, joules. Yikes. Right? And we know what K1 is. We already calculated that, 150 joules. We know what U1 is. K3 and U3. K3 is 1/2 mv3 squared. That's what we're trying to find. That's unknown. What about U3? Potential energy at the bottom. Well, that's equal to 0 joules. Okay, so here's what we have. We have K1 plus U1 plus work other equals K3 plus U3. Okay, so U3 is 0 and U1 is 0. Okay, and so that means K1 plus work other equals K3. All right, and so let's just flip that around. K3 would be equal to 150 joules. That's K1. Plus work other, which we found is this negative 112 joules. And so 1/2 mv3 squared is equal to, this I think is 38 joules, the net there. Right, and so that means V3 is just the square root of 2 times 38 joules divided by the mass, which is 12 kilograms. Right, and you do that math and you see that it's 2.5 meters per second. So the thing starts out with what, 20 meters per second or 5 meters per second? Yeah, sorry, 5 meters per second. Yeah. Slides up the ramp to a stop, and then gravity pulls it back down the ramp, but it doesn't, by the time it hits the bottom of the ramp, it doesn't have nearly the velocity that it had initially. It doesn't, it's about half. So it starts out with 5 meters per second velocity, and it ends up at 2.5. Right, and that's a result of the friction. The friction is causes the kinetic energy at the bottom of the ramp to be less than the kinetic energy at the top. The total mechanical energy is less at 3 than it was at 1. Okay, all right, very good. That was an introduction to the idea of potential energy, specifically gravitational potential energy. Now in the next lecture, we'll discuss a different kind of potential energy, and that is the elastic potential energy. All right, until then, take care.